So first of all, it's a pleasure to be here. I'm very happy the organizers kindly invited me to give the lecture. I was told that there are about 50%, maybe not exactly 50%, but a lot of physicists and a lot of mathematicians, both. So I tried to design a talk that would reach both audiences. It's also going to be given in dual style. So for the physicists, I have slides. And when I need to do a little bit of math, I'll use the boards. Okay, so first of all, let me just start off with a little bit of background. So my talk is going to be semi-historical, and it's going to explain where this concept of spontaneous stochasticity arose. And in physics background, it's related to the mixing and dissipation of advected scalars in a turbulent flow. So it's known that you have a so-called dissipative anomaly, not only for kinetic energy in a turbulent flow, but also for the analogous dissipation of the scalar intensity. Okay, so that is, when you look at this equation for the passive scalar here, if you look at 1/2 c squared, that's called the scalar intensity. It's the analog of kinetic energy. And its dissipation is given by the diffusivity times the gradient of the concentration field squared. So for example, you can put a drop of dye into a stirred glass of water, or you can put perfume or cologne into the air of a turbulent auditorium, and you will experience turbulent mixing of that advected scalar. And here's some evidence from a very nice paper of Danzas et al. In 2005, 20 years ago, but it still has a very nice compilation of both experimental and numerical data showing that if you scale, they call the scalar phi, but if you scale it with its you scale the dissipation rate with the RMS squared of the scalar, the integral length, and the velocity fluctuation, the RMS velocity, then in the limit of large Reynolds number, this becomes constant. So actually you're taking a limit of both Reynolds number getting large, also the so-called Peclet number very large. That's analogous to Reynolds number, but with viscosity replaced by the diffusivity. You're holding the Schmidt number fixed, which is natural because both of these are fixed by molecular kinetics. And so when you increase the Reynolds number, generally for a given fixed fluid, this quantity is fixed. And in that limit, this is actually evidence from numerical simulations, but this paper has a whole compilation of evidence from both laboratory experiment and from numerical simulations showing that this quantity becomes independent in the becomes constant and non-zero in the limit of large Reynolds number and large Peclet number with their actually Schmidt number for concentration. Peclet number if you're looking at temperature. They looked at both temperature fields and concentrations. But anyways, it becomes almost independent of Reynolds number. So this is the so-called dissipative anomaly for the advected scalar.
Yes, in your notation, phi is C.
Yeah, so this is taken from their paper where it was phi. That's my C. And again, in their paper, they considered data both from binary mixtures in which it was the concentration, and sometimes also it was the temperature field.
And the variance of the scalar is independent of D too?
It doesn't have to be. I mean, in fact, this is an issue in general that, I mean, as you increase the Reynolds number, the notion of anomaly depends crucially on the correct non-dimensionalization. So in some cases, if you had, for example, no advection, and you simply had dropped the advection term completely, if I inject a constant amount of scalar, well, of course, the mean concentration, the dissipation of the scalar is independent because in a steady state, it's directly related to the injection rate. But in that case, you don't have a dissipative anomaly because the variance would grow without bound in the infinite Peclet number limit. And so it's really crucial then that you see a constant when you non-dimensionalize by this quantity. In that case, for the pure diffusion equation, this would go to 0. Yes. Okay, so this concept of spontaneous stochasticity arose in this 1998 paper by these authors, Bernard, Gawędzki, and Eyink. They were trying to do many things in this paper. This is a very rich paper. But one of the things that they came up with was a novel explanation of the origin of this scalar dissipative anomaly. And as I underlined here in the abstract, they realized for the first time that this dissipative anomaly for scalar mixing is directly related to what they called non-deterministic behavior of the Lagrangian trajectories at high Reynolds number. Okay, and that's what I want to explain is this connection, which is what we now call spontaneous stochasticity. By the way, there's also a paper, actually you can't see all of my talk, a little bit is here. So some of the references you can't quite see, but I have some other references down here, including there was a, pardon?
Maybe we can...
Oh, maybe I can solve this manually. That solves that problem, okay, yeah. That's a manual fix, okay. Yeah, so now you can see it. Okay, so in fact there was a preprint by just Krzysztof Gawędzki alone in 1997 that talked about this independent of the others. And I should say Krzysztof in particular really emphasized the importance of this in many, many subsequent articles and lectures that he gave. Okay, so what is this basic idea? Well, first of all, they realized that there's going to be, I mean, it's well known, in fact, that there's a breakdown in uniqueness for the Cauchy initial value problem in a rough, merely Holder continuous velocity field. So in general, if I have a velocity field that satisfies this Holder condition here with h equals 1, which is technically called a Lipschitz condition, then you have unique solutions of ordinary differential equations for arbitrary initial data. But if h is less than 1, you can have non-uniqueness. And in fact, it's a consequence of something called Kneser's theorem, that whenever you have non-unique solutions, there's in fact a continuous infinity of non-unique solutions. So you never just come up with 1 or 2 or 3. When you have non-unique solutions, there's always a continuous infinity of them. In dynamical systems language, that means that these systems have infinite Lyapunov exponents, because now you get separation even though you take the initial separation of the particles going to 0. So since if you think about the way you define Lyapunov exponent in terms of the spreading as you let the particles get closer and closer together, if you divide by that separation, and if they separate even as the separation goes to 0, that means the Lyapunov exponents must diverge. Okay, now this is relevant to the problem because when you're looking at how little parcels of fluids move in a fluid, they follow the local fluid velocity u. And that means that this is directly relevant to Lagrangian mixing, in particular in the infinite Peclet or Schmidt number limit where the diffusivity is vanishing. But it was pointed out by Onsager in 1949 that for other experimental reasons, the velocity field in a turbulent flow cannot have a Holder exponent bigger than 1/3, otherwise kinetic energy dissipation vanishes. And so then the question that was addressed by these authors is, how does particle motion affected by such roughness of the advecting turbulent velocity field? Okay, now the essence of this can be easily understood from a very simple model. And mathematicians, or anybody that's taken a good course in ordinary differential equations, will immediately recognize this simple toy model as the standard example given in every good ODE text about the necessity of some condition for unique solutions. So this is the standard counterexample that shows that if you weaken the conditions, the Lipschitz condition, a little bit, you no longer have unique solutions. So here, in this example, the advected, we're just going to take a one-dimensional example. We'll let R be the difference in the two solutions, solution 1 and solution 2. And our advecting velocity field is going to be now 1/3, and we're going to consider just the relative motion of these two particles. And this you can think of as a toy model of the Kolmogorov-Onsager 1/3. Well, since it's just a one-dimensional ODE, you can easily write out the exact solution by separation of variables. This is an undergraduate exercise. Here's the answer. First thing that you see about this solution is that if you look at very long times, bigger than this time here, given by the initial separation and by this parameter in the velocity field, they define together this characteristic time t0. So if you look at times much longer than that characteristic time, then you completely forget the initial separation, and you see this t-cube behavior. So the initial separation of the particles in this little toy model is completely forgotten at long times. Correspondingly, if I let that initial separation go to 0, then I don't go to 0, and I still separate to finite time. And that's because in this problem, I have a multiplicity of non-unique solutions. There's one solution of this problem in which I follow this behavior, well, actually the square root of that. Another solution which I just stay at rest. I just stay at the origin. R remains 0. And I have a continuous infinity of solutions depending on, in this case, parameterized by the amount of time that I spend at the origin before I start departing according to this law. Okay, so this gives us a very simple model in which we can understand how the roughness of the advecting velocity field affects the particle motion and can lead to non-uniqueness. Okay, now people from the physics community, in particular the physics of fluids community, will immediately recognize that this t cubed is the same that was proposed by Lewis Fry Richardson back in 1926. This is what's called the Richardson t cubed law. And Richardson arrived at this result semi-phenomenologically by looking at observations, among others, by spreading of smoke plumes. He looked at a whole variety of data, including related to buoys on the surface of the ocean, volcanic smoke plumes like this one. And by looking at that empirical data, and by using some magical intuition that only Richardson had, he came up with this t cubed law. In fact, he worked out a diffusion equation, a so-called scale-dependent diffusion equation, and came up with a similarity solution. And that similarity solution is an asymptotically valid solution at long time of his similarity equation. And it exactly has this forgetting of the initial data built in. So in some sense, Richardson implicitly had in his 1926 theory the elements of what we now call spontaneous stochasticity. Okay, so it's really this forgetting of the initial data which is an essential ingredient of what's called spontaneous stochasticity, physically. Yes? Pardon? You could have spontaneous stochasticity without 1/3, and in fact, in the Kryknon model, for any exponent between, Holder exponent between 0 and 1, you would get spontaneous stochasticity. I was just trying to keep the example as close as possible to incompressible fluid turbulence, where even this little simple toy problem recovers the Richardson t cubed law. Of course, you guys have to work a lot harder to get it. Yeah. Okay, now, as far as evidence for some of these basic requirements, they have been seen in numerical simulation. So in particular, I'm talking about this forgetting of the initial data. In fact, this is from a paper of Battani, Hohmann, and Jeremy Beck. Jeremy Beck is also here somewhere. He's going to speak later this afternoon, I think. And so this is from a numerical simulation that they did of particles in incompressible homogeneous isotropic turbulence in a periodic box. And what they did is they seeded the flow with little pairs of particles, and they allowed the initial separation of the particle to change. And what you see is as you let the initial separation of the particles, here non-dimensionalized by the Kolmogorov length, and as you let that initial separation go to 0, what you find is that you bend over to the same t cubed law, and that t cubed law is reached asymptotically independent of the initial separation. So physically, this is an essential ingredient of what we now call spontaneous stochasticity, is this forgetting of the initial data at long times. And they saw this in 2 different simulations at higher Reynolds number. I should say, experimentally, it's an embarrassment that we still have not seen this convincingly from experiments. This has been an ongoing issue in terms of experimental turbulence research for 20 years, that this kind of T-cube law and a clear, unambiguous forgetting of the initial separations has still not been seen in laboratory experiments. This seems to be just an experimental issue with the difficulty of tracking many, many particles with initially very small separations. So the natural thing to do is fill your turbulent flow full of lots of little particles so you get good statistics. But then the problem is that when they're very close together, you have to track individual particles over long times, not mistake one particle for another particle. It's very tricky. Okay, so it's still not been done experimentally just because of the difficulty of tracking the particles. But from numerical simulations, we have good evidence.
It's also because they are working with a closed flow also, no?
Well, maybe for a, I don't think that's a problem. This is in a periodic box, right? So I think you have to have a long enough inertial range. They can reach higher Reynolds numbers than these experimentally. So you can get a good long inertial range, well before the particles reach the size of the system. So I don't think the closed box is the real problem. It's just the problem of distinguishing particle A from particle B, because you have to be able to look at the differences between pairs of particles, and you have to not be able to mix up, if they cross later, particle A with particle C that came close to it. So how do you distinguish the different particles when they're densely seated in the flow? That's the real problem, as I understand it from talking with the experimentalists.
The typical standard statement in turbulence theory about separation of velocity is that it scales with the distance to the 2/3. That's a statistical prediction, a statistical result. If you measure many velocity differences that form a moment, you get this. This is a theory for very specific realizations. Is there a...
Well, of course, the data that I'm showing you here is averaged over the entire flow. So in that sense, this statement is not for just one pair of particles. You could ask Jeremy about the details of this, but in fact, they looked at many, many particle pairs distributed over the whole flow and then averaged them. What you should emphasize here, that it's enough to see, in fact, in the original work of Bernard et al., it's enough to average over an ensemble of velocity fields. Because if the separation goes to 0 for one fixed velocity realization in the limit when the particles go to 0, then you can average over the ensemble and it still goes to 0. Right? So if in every single realization, if you take the pairs of particles closer and closer together, and if that separation ends up going to 0, then when you average over the ensemble, it doesn't change it. Right? So in the original work of Bernard et al., they predicted spontaneous stochasticity by exactly looking at the probabilities of many particles, but averaged over the velocity field. And what they observed from the exact solution of the Kryknen model is that when you let the initial separations to go, those transition probabilities do not go to delta functions. But that immediately implies that it cannot be true in individual realizations, right? So in order to establish this phenomenon, it's enough to look at quantities averaged over velocity fields. But you're right that the statement is that the trajectories can't be unique in fixed realizations of the velocity. But you can infer that by averaging over ensembles. Okay, is that clear? Okay.
Are you thinking about intermittency or non-Gaussian stuff or no?
I don't know.
No?
Well, I'm saying, but you can rigorously infer that they're not unique for individual realizations by studying the properties averaged over an ensemble, right? Because if, it could be in the Kryknen model, this is not true, but it could be that with with some finite probability, they are unique. And that when you let the initial particle trajectories go to zero, that with some finite probability, the particles do stay stuck together. But in the incompressible version of the Crichton model, that's known not to be true. And maybe only with some finite probability do they split. But you can rigorously infer that with some finite probability, they have to split by looking at these ensemble average quantities. Okay. Okay, now you can also see this same forgetting. In fact, I did this even earlier. This is using the Hopkins turbulence database, our original one. This is that now minuscule Taylor scale Reynolds number of about 430. This was a 1024 cube simulation. But here what I did is I did not put in deterministic fluid particles and then allow the initial separation to change. What I did is I started all the particles off at the same position, but I added noise to the particles, and what I find is that as I change the noise, you forget the noise strength added to the particle. So here's two different choices of the noise, differing by a factor of 10. And what you see is that independent of the noise at long times, you always bend over to that same T cubed law. So in this case, you don't forget the initial separation. The particles are starting off at exactly the same point, but at long time you forget the actual value of kappa. And in this case also, I looked at many, many different particles distributed over the flow. This is an average result, averaging over the initial position of release. Okay.
But since U is Lipschitz, because you are at a finite...
But I mean, but it matters whether it's uniformly Lipschitz, right? So the problem is, yes, in the real world, velocity fields are always, well, maybe there isn't an actual velocity. That's a different question. Richardson questioned that, and I questioned it too. I don't believe in this mythological actual velocity field. But even if you believed in that, what matters is not just whether it's Lipschitz, but whether the Lipschitz constant is uniform in the Reynolds number. And what we know about turbulent flow is that the Lipschitz constant is not uniform because the velocity gradient blows up in the limit of large Reynolds number. So really, when you're talking about actual spontaneous stochasticity in a real physical system, of course, it is Lipschitz, but it has to remain uniformly Lipschitz. In order to get a unique solution in the infinite Reynolds number limit, it has to remain uniformly Lipschitz in the limit as Reynolds number gets large. Okay?
My point is to say you can study that equation with kappa equals 0.
Oh, I mean, I could in this case, and in this case, if I did that, then if I set kappa equals 0, I'll be back at looking at deterministic particle trajectories, and then there will be no spreading, right? Because what I'm doing here is I'm looking at the separation over, so this is for every single particle, I look at an ensemble of stochastic trajectories separating from that initial point. If I set the diffusivity to 0, then within that ensemble, there'll be no separation. And then, if afterward I average over the position of the particles, it's still 0. Okay, so of course you're right, I cannot in this fixed Reynolds number flow take the limit of kappa going to 0, because then I would not, I mean, then my Schmidt number is also diverging, or my Prandtl number, since I'm using kappa. Right, so I should consider a limit of fixed Prandtl number, finite. Actually, it's known that in the infinite Schmidt number limit, which is the regime of the Bachelor, the passive scalar, you don't have spontaneous stochasticity. Right. Okay, although that's a little delicate. Yes? The one before this? So these are large-scale stirred flows in a periodic box, homogeneous isotropic turbulence. And Jeremy Beck is somewhere here. There he is. You can ask him all the details about the simulation. but it's standard homogeneous isotropic turbulence in a periodic box. And then they release pairs of particles and then average over many, many pairs of particles at different separations. Okay, and the point is that as you let those separations get very, very small through the inertial range, by the way, this goes back to the question that Laurent was asking. If I let these initial positions go below the Kolmogorov scale, then there will be an initial period of exponential growth, because then I'll see standard chaotic error growth. Of course, once that pairs of particles, once they reach inertial separation of order the Kolmogorov range, then I switch over to this. Okay.
At larger time also you expect...
And a longer time, eventually, I mean, this I cut it off once it reached the integral scale. If I go to longer times, then of course, if in a really big box, once it beyond the integral length, then it would become linear. That's standard Taylor diffusion. And once it reaches the box size, it will saturate. But I'm only interested here in this intermediate asymptotic regime. That's the important thing for this discussion. Okay. So now, again, I said that Bernard Gawędzki and Kupiainen were interested in understanding the mechanism of anomalous dissipation of the scalar. And there is a direct connection between the Lagrangian particles with this stochastic perturbation that I just mentioned in the previous slide, and the scalar advection diffusion equation, because you can use the so-called Feynman-Katz representation of that diffusion equation. And so what Bernard and al. Looked at was, in fact, the statistics of these stochastically perturbed particles. Actually, you can think of this as a mathematical trick for introducing diffusion into the problem. This is no mathematical trick at all if we're talking about diffusion of a concentration like perfume, because then you actually have individual perfume molecules, and this D is representing the actual physical Brownian motion of the individual perfume molecules in the flow. And so then this is actually the physical motion of a perfume molecule. It is both advected by the turbulent flow, and it also undergoes physical Brownian motion. And in that physical Brownian motion of the individual perfume molecules is the origin of the macroscopic diffusion that we see of the drop of dye or the little spray of aerosol that I put into the room. Okay, so that's the reason that they were interested in studying this random advection equation, which is now a stochastic differential equation. You can write down a formal path integral solution of that equation. This has been done in many times in the physics literature. I think Strymon and Sidger were among the first, but there were also other people in other contexts that use this. If you're a mathematician, this is completely rigorous. It's just the Gersonov formula. Okay? It's the Gersonov formula. Okay, so the Gersonov formula actually tells you, if you look at the solution of this stochastic differential equation, then you can write down its path measure in time, as over time histories. And the Gersonov formula gives you the Radon-Nikodym derivative of that distribution relative to the Wiener process. And that's the way that you can actually make mathematical sense of this path integral expression. So it's perfectly kosher mathematically, but this is the way that physicists usually write it, because then it becomes intuitively clear that in the limit where diffusivity goes to 0, you would expect that this has to be concentrated on solutions of the deterministic ODE. And as we all know, that is in fact exactly what happens if this velocity field remains uniformly Lipschitz as nu goes to 0. And this is the origin of standard Friedland-Wenzel large deviations theory. So then, as d goes to 0, with probability going to 1, I just see the deterministic solution of this equation, and then there are central limit theorem corrections to that, little Gaussian fluctuations, and also large deviations away from that. And that all just comes from a steepest descent approximation of this path integral expression. But that's not the situation that happens in a turbulent flow, because even though this velocity field is Lipschitz, as Lorenz said, for fixed nu, we're taking a limit both of kappa and nu getting small together. And that means this velocity field is not uniformly Lipschitz. And what they realize is that when it's not uniformly Lipschitz, as you let nu and d go to 0 together, this ensemble never has the slightest tendency to go towards a deterministic trajectory. So by the way, this is saying this is not a phenomenon that appears suddenly at infinite Reynolds number. What this is saying is that the randomness persists in the limit as you let nu and kappa, or nu and d, go to 0 together. It never has the slightest tendency ever to become deterministic. Okay? So you don't need to go to the limit to see the phenomenon. And so precisely what they argued is that in fact this does not go to a deterministic distribution on a single trajectory. It stays random. Yes?
What happens if they go to 0 but not together?
It depends on how you do that. In fact, if you take nu going to 0 first, then all the phenomena that we just talked about is still true if I take kappa to go to 0 subsequently. If I do the limit in the other order, it's a little bit more delicate. So if I let kappa go to 0 first, then I have deterministic ODEs. There's no longer any source of randomness. However, if you allow the initial data in that case to be slightly random, and now you let the randomness in the initial data disappear together as the viscosity goes to 0, then in this model, the Crichton model that they analyzed, I'll talk about that in a moment, you get exactly the same spontaneous statistics. So it is slightly delicate if you take kappa go to 0 first, then you need an additional source of randomness, which would be randomness in the initial data. Okay, and so exactly they pointed out that this is possible, that you can get this non-vanishing statistical behavior. The solutions of the equation can remain random precisely because there are no longer unique solutions of the limiting equation. And in fact, what you get is a random distribution over ensembles of these non-unique solutions of the limiting stochastic equation. Okay, so this is the picture. This is like a cartoon, yes? What is capital? I'm sorry, what is? Sorry. Okay, so mathematicians should close their eyes when I say anything like that, okay? This is what physicists do, okay? This is the kind of thing that, they try to scare mathematicians away, okay? Because we know that there is no such thing, okay? But I can still make sense of this. So, if I really want to do this correctly for a mathematical audience, I need to square this out. When I square this out, there's one term which is this x dot squared. When I combine that with this infinite Lebesgue measure, I get the Wiener measure. And in fact, if you think the way that Wiener actually produced that measure, he discretized time, and then you have a high-dimensional Lebesgue measure multiplied by a bunch of Gaussians. When you take the continuous time limit, you rigorously get Wiener measure. And you can actually make sense of this in a completely kosher mathematical way by squaring this out. Then you get a Wiener measure with a density, a Radon-Nikodym derivative, and that Radon-Nikodym derivative is just the one given by the Gersano formula.
But dx is on both sides, you can just cancel it.
Pardon?
Dx is on both sides.
Yeah, if you like. But really, this only makes sense if I put the dx on both sides mathematically, right? I can't make rigorous sense of the result unless I put the dx. Okay, so the cartoon, the simple explanation, this was actually a diagram that was made by my then PhD student, Theo Drevis. He saw this is a really nice way to illustrate this. In a standard ODE, so that if I let viscosity go to 0, but if my advecting velocity field stays smooth, then I'm in the regime of standard Friedland-Wenzel large deviation theory. And as I let d and nu go to 0 together, all these random trajectories almost shrink to the deterministic trajectory. And at finite d and nu, there's still a little bit of randomness, but to leading order, that's a central limit theorem correction. And then if you look at things way out here, far away from that, there's a large deviations probability. That's standard Friedland-Wenzel. But what happens when you have spontaneous stochasticity is that standard Friedland-Wenzel large deviations asymptotics breaks down because the advecting velocity field is not smooth enough, not Lipschitz, to guarantee a single saddle point. You actually, in principle, have infinitely many saddle points in the limit. Standard Friedland-Wenzel asymptotics breaks down, and in the limit, as you let the noise and the viscosity, the diffusivity, which now also represents the Brownian motion, the noise, as they vanish together, you still end up in the limit with non-trivial probability, because each of these limiting solutions has a different probability from the other, and all the remnant stochasticity is associated with probability distribution over those limiting non-unique solutions. That's what spontaneous stochasticity is. As I'll discuss in a later lecture, there's actually, I think physicists can already see this, but there's actually a very close analogy to zero temperature phase transitions in situations where you have infinitely many ground states, or non-unique ground states. They don't have to be infinitely many. And in fact, in that case, this action, this is, by the way, it's also called the Onsager-Machlup action. This Onsager-Machlup action is the analog of the Hamiltonian for an equilibrium statistical mechanical system, and then D is the analog of the temperature. And so you can think of this as looking at the zero temperature limit for a problem that has non-unique ground states. By the way, when I first talked with Krzysztof Gawędzki in 1997 at IHES, when he first told me about this, exactly he made that point. Okay, so that was exactly Krzysztof's point of view, is that there is an analogy of this problem with such statistical mechanics systems. Okay, now the term spontaneous stochasticity for this phenomenon seems, from discussion with the people involved, to have originated in this review article by Falkovich, Gawędzki, and Vergasola. And here's the direct quote from their work. This spontaneous stochasticity of fluid particles seems to constitute an important aspect of developed turbulence. And they drew pictures much like this to illustrate the phenomenon. Okay, so let me explain then how you can get anomalous dissipation out of this Lagrangian spontaneous stochasticity. It's more or less a direct result of the Feynman-Katz representation. So I can solve this equation here by using the heat kernel associated with this diffusion term. And in this particular problem, again, I can write out this transition probability for the stochastic advection diffusion equation that I wrote on the previous slide. This transition probability has this path integral representation. But the Feynman-Katz representation says that I can solve this advection diffusion equation by using these transition probabilities for the stochastic ODE. And I will give you a short, if you're not familiar with this Feynman-Katz representation, I'll give you a short proof on the next slide. But this says that I can represent the solution of this equation at time t by averaging over the backward trajectories of this stochastic ODE that start at x at time t and end up at arbitrary random x0 at the initial time. And then by sampling the initial data and averaging over those random probabilities, that exactly gives me the solution to this advection diffusion equation. So again, that's a rigorous way of representing the solution of this equation. And now we can consider in this case the limit as nu and d go to 0. If this transition probability does not collapse to a delta function, then it follows immediately by convexity that, so again, since this 1/2 c squared is a convex function, in fact, it's a strictly convex function, if this p star is not concentrated on a single atom in the language of probability theory, then this convex function can only decrease under averaging. And so I can see immediately that if this thing is spontaneously stochastic, this average must decrease in time. But I can also go in the other direction, and I can say that if this decreases in time, this cannot be a delta function. Okay, and in fact, that takes a little bit more argument because you have to show that this diffusion process actually converges conserves the Lebesgue measure, but that can actually be proved in this model. And so in this model, you can also go in the other direction, and you can say that if there is spontaneous stochasticity, then as a matter of fact, this has to not be a delta function. Okay. Okay, now, in this model, and this goes back to one of the questions that was asked earlier, it's actually known that this spontaneous statistics is very robust. And it's largely independent of how I add the external randomness. I can add it through external initial data. I can regularize the velocity field in many different ways. I can take the limits in many different orders. And I always get the same spontaneous statistics. And that was proved rigorously in this very nice set of papers by probabilists Lejeune and Ramon more than 20 years ago. And I'm a little short on time, so I think I'm going to not try to sketch the proof. But essentially what they did is they realized, I'll just say a few words. They realized that if you want to solve the stochastic ODE, well, how do I say it? Yeah, if you want to solve this, ODE, okay, this is going to take too much time because I have to explain Stratanovich to Ito. Okay, if people want to hear about it, I will explain it privately. But in any case, what they did is they realized that you could write out an exact formula for the limiting transition probabilities at fixed velocity fields. So this goes back to what Oliver was asking. You can fix, in this Krykman model, a fixed realization of the velocity field, and they could rigorously construct the Markov transition probabilities of the random trajectories. And they could show that they are non-trivial Markov processes that are not concentrated on a single atom. Okay, and the way that they did that was by using a what's called a Wiener chaos expansion, a particular version of it called Krylov-Retnikov expansion. And they could therefore, because they could do this without any specific regularization at all, then it's very easy to show that by adding different regularizations, you always converge back to that result. So they actually constructed this limiting, spontaneously stochastic process with no regularization. They just wrote down the exact solution by using a Wiener chaos expansion. They showed that it converged in L2, and then they showed that you get that from any reasonable limit. Okay. By the way, what that means that in this problem, the well-posed problem for following particle trajectories in this model is not to ever try to find one unique particle trajectory. The correct well-posed problem in the sense of Hadamard is only to calculate the probability distribution of the particle trajectories. That problem has a unique solution, which is also stable under perturbations, and that's exactly what's proven in these papers. So that means that this fundamentally changes what is the correct well-posed problem. The ordinary Cauchy initial value problem is not well-posed. It has many, many non-unique solutions, but there is a unique solution for the probability distribution on these non-unique trajectories, on these non-unique solutions. Okay. By the way, before I leave the Krykman model, I just want to raise one question which, as far as I know, has not been answered, and that's about spontaneous stochasticity of flows. So it's known that if my velocity field is smooth, then in fact, if I solve this Stratanovich equation, I get actually a flow map. In fact, in the case where the velocity field is divergence-free and smooth, it's a set of volume-preserving diffeomorphisms, and it's a one-parameter group of them. As Lejeune and Watanabe showed in an earlier paper, more than 40 years ago, this actually defines a Brownian motion on this group S-diff of infinite, the whole group of volume-preserving diffeomorphisms. Now that's true in the case where the limiting velocity field is smooth. But what about in the Kryknon model where U is only Holder continuous? It's a fundamental question. Do those flows have a limit in some sense? This is a tightness question on the probability distribution on those set of diffeomorphisms. I don't know if I don't think there's an answer whether you can form a limiting distribution on this random set of diffeomorphisms. This actually has really interesting consequences. If that flow does exist, then the n-particle process that was studied by Lejeune and Ramon just corresponds to the random process that you get by looking at the initial data AI and then just advecting them according to this ensemble of flows. But if this set of, they're certainly not going to be diffeomorphisms, or probably not, because the velocity field is only Holder continuous. You expect they might be homeomorphisms. But if that's true, then you can also advect higher dimensional objects like loops. And if there is a random distribution over this set of homeomorphisms, then these loops will advect into other ensembles of loops in time. Whereas if that's not true, then this thing would just explode into a cloud of particles. Okay, so this is, as far as I know, an open, I talked with Lejeune about this like 10 years ago, and he didn't know how to tackle it. But this is, as far as I know, an interesting open question about the Kryknon model. Okay, now let me turn to the general scalar advection problem, because in the paper of Bernard et al., they emphasized in that paper and later papers that many of their considerations of the Kryknon model are very general, and they don't depend on the detailed feature of the Kryknon model. Okay, so the Kryknon model, again, is this model where the velocity field is Gaussian and delta correlated in time. So this is what probabilists call a Brownian flow. Okay, but many of their conclusions don't depend on those assumptions. So let's just consider first a general advection velocity field. And again, I can look at the flows, the stochastic flows, with this extra added noise. And what I'm going to do is I'm going to give you a quick derivation of the Feynman-Katz representation. And in fact, the easiest derivation is not using, I think, the path integral methods that physicists prefer. The much easier way of doing it is just using backward Ito equations. And if you don't know backward Ito equations, you do, because they're exactly the same as forward Ito, just reversing time. You just take forward Ito and you reverse time and you get backward Ito. Okay, so you can take this equation, interpret it as a backward Ito equation, and then I can apply the backward Ito chain rule to this random flow map inside theta, where theta is the solution of this equation. And when I just directly apply backward Ito and the chain rule, I get this. That's an easy computation. People that know Ito know that Ito gives a plus here, but that's because we're reversing time, so now it gives a minus. Well, if I take that this is the solution of my equation, I can just substitute here S for this quantity. And so this quantity, when I look at its backward differential, backward Ito differential, I just get this, which is clearly a backward martingale. And in fact, if I integrate in time, then this is a backward Ito integral, which is in fact a backward martingale. And that means that the expectation of this is conserved in little s. And so in particular, if I take the expectation, I will get the initial value. So the expectation of this will be the initial value. That will give the Feynman-Katz formula on the next slide. Here I'm making even a stronger statement. This is the statement that it's a backward martingale, because if I take the expectation of this quantity conditioned on some values of that Brownian motion over this time interval, then I just get the last known value, which is, actually, did I do this right? Oh yes, it's the last known value is this value r, so last going backward in time. So this is the statement of being a backward martingale. And by the way, this means that we know that for ideal flow, then when I have no diffusivity, the value of this scalar is just conserved along the velocity field. It's conserved along the characteristics of that hyperbolic advection equation. This is the generalization of that statement when I add diffusion. So this Feynman-Katz representation is also known in the literature as a stochastic method of characteristics, and it generalizes the usual method of characteristics from hyperbolic equations to parabolic equations. Okay, so now I can state what I said in words. I can write the formulas. If I want to get theta x, that's at the earliest time, and if I take an unconditional average, well then my earliest time that I specified was just t itself, and so then when I take this average, I get theta xt. That's at my time t that I started at and then went backward in time from. And so I can now substitute in my definition here of this quantity, and that directly gives me what's called the Feynman-Katz representation of this advection diffusion equation with this extra source term. So for greater generality, I also added a source S for the scalar, so that means I'm pumping dye or temperature into the fluid with this S. Okay, and again, if I compare that with the ideal flow, you now see there's a very close comparison. If I look at the ideal flow, where there is no diffusivity, then by characteristics, these are the characteristics for this hyperbolic equation, I can just directly write the solution of this equation in terms of those characteristics, like this. And now you see that the Feynman-Katz representation directly generalizes that representation for hyperbolic equations to the corresponding representation for parabolic equations. Okay, so this is the basis in which you can understand the generality of the arguments of Bernard et al. In particular, that argument based on convexity only depends on two things. It depends on the convexity of 1/2 c squared, and it also, or here 1/2 theta squared, I'd flip notation now. But it depends on the convexity of that. It also depends on the limiting transition probabilities conserving Lebesgue measure. It turns out that that conservation of Lebesgue measure can be proved in great generality by using techniques of Young measure. And so that argument of Bernard et al., in fact, works completely in general, and you can conclude in free decay the only way, absent boundaries, so all of this is away from boundaries, absent boundaries, the only way that you can ever get for an incompressible flow anomalous dissipation of scalar is by Lagrangian spontaneous stochasticity. There's no other way it can happen. That's the only possible way. And this conclusion is true even if you add a source term in, and that's what we discussed. Actually, there was an earlier work by these authors, which we didn't know about. Theo Drivas independently discovered the main identity that they derived, and then afterwards we found, oh, of course, somebody else had noticed this nice fact. But if you add a source term, you can go back and use this equation that I had on the board previously, and I can take this theta tilde, and I can now take remember my definition of my theta tilde, I'm just subtracting this term over to the other side. And when I do that, I can now take the variance of this, even in the presence of a source, and I can show that the variance of this quantity is directly related to the viscous dissipation by Ito anisotropy. And so what this formula tells us is that if I have anomalous dissipation and the limit is kappa and nu go to 0, that's studying this term, that can only remain non-zero if the variance of this stochastic quantity here remains non-zero, which can only happen if the trajectories stay random. And in fact, this allows us in this paper, using also a little bit of Young measure theory to handle the incompressibility and the conservation of volume, to make all that argument into a rigorous proof. Okay, so what Bernard et al. Realized is very general, which is that the only way you can get anomalous dissipation for incompressible flow away from boundaries is if the particle trajectories remain random in the limit. Okay, now there are nowadays lots of rigorous examples of anomalous scalar dissipation. So here is a list of constructions of velocity fields for which there is anomalous dissipation. Armstrong and Vickel are in fact lecturers that you will hear from at length about their particular construction. And I'll just mention that one of the really important things about the construction of Armstrong and Vickel is that for the first time, the advecting velocity fields, and this is very unlike the Crichton model, have correct sweeping properties. That is, large eddies in the flow sweep the small eddies. That's not true in the Crichton model, and it's responsible for certain fundamental differences of the Crichton model from actual real turbulent flow. And so that's an important advance made by Armstrong and Vickel that you'll hear about. Following up on their work, these authors added an extra 50 pages of work combining it with convex integration methods, and they showed that you can even construct weak solutions of Euler equations that exhibit anomalous dissipation of the scalar. And of course that means that these weak Euler solutions have to exhibit Lagrangian spontaneous stochasticity. Now, one of the issues that I should have mentioned actually when I went back here is that this argument that I made with Theo in this paper, I skipped over this. It was written here, but I didn't emphasize it. In this argument, there was no implication about the robustness, the universality of the spontaneous statistics. So in the Crichton model, it can be shown that many different ways of taking the limit always give the same limiting spontaneous statistics. This argument based on anomalous dissipation does not have such an implication. When we say spontaneous stochasticity here, we only mean that the limiting trajectories must remain random. There's no statement that that limiting randomness must be the same no matter how you take the limit. So there's no universality statement in this general argument here. And indeed, that has come up in lots of recent work. In fact, all of these papers that I mentioned here also raise the issue. In fact, you can see that in many of the titles, is that they also raise the issue whether the zero diffusion limit is actually a good selection principle for the limiting weak solutions of that hyperbolic advection equation. And the answer turns out in these constructions to be negative. And I think the first paper that I'm aware of that addressed this was these authors, in which they didn't look at adding diffusivity, they looked at smoothing the velocity field. But then that was followed by all these other papers that showed you can also get similar results by adding diffusion. And what is known now is that you can get different limits as you go along different subsequences of nu and kappa going to 0. And in fact, you can get quite remarkable things. You can get along one subsequence anomalous dissipation, along another subsequence no anomalous dissipation. These authors, Huisman and Titi, even constructed a velocity field in which the solution unmixes. So it's anti-dissipation. It unmixes. It mixes and then unmixes. So you can get a lot of weird phenomenon going along different subsequences. And that shows that although the argument that Theo and I gave says that when you have anomalous dissipation, that requires spontaneous stochasticity, there's no statement that it must be universal. Okay. Now you can apply, so the mathematicians will know the superposition principle of Ambrosio and Crippa, and you can actually use that to deduce non-unique particle trajectories, but without any statement about uniqueness. Okay, so what should we really call Lagrangian spontaneous stochasticity? This is just a question of terminology, but terminology in the end does matter. I don't like to say we should call this spontaneous stochasticity, we should call that spontaneous stochasticity, but at the very least we have to make an important distinction. And the point is that when I look at the general problem, there are at least two possibilities. One is what happens in the Kryknon model, whereas when I take the limit, I can get I can get a limiting measure, which is some superposition of trajectories on a given trajectory. That's what I'm indicating here. This x omega is the whole time history now. So one particular atom in this function space. So I can get that, but there are at least two possibilities. One is that I get this thing which is not a delta measure, it's actually a non-trivial superposition, but it's the same no matter how I take the limit. And I think that should be called something like robust spontaneous stochasticity, and that's what happens in the Kryknon model for incompressible velocity fields. On the other hand, as we see in some of these other examples, you can also have what I would call fragile spontaneous stochasticity. That is, you can along subsequences get distributions which are not supported on a single trajectory. It's some non-trivial superposition, but it might not be the same measure for every different sequence. Every different subsequence might give a different limiting measure, and in fact, along some of those subsequences, it might actually be a delta measure. Okay, then I would say it was some kind of fragile spontaneous stochasticity. Okay, so these examples show that that can happen, and I should emphasize that in fact, even in the Kryknon model, it's known that if I look at compressible velocity fields in an intermediate range of compressibility, then I also get this fragile spontaneous stochasticity, and that was discussed in these old papers 25 years ago, in which they showed, depending on how you take the limit with the Schmidt number, you get different kinds of limiting trajectories. In some of them, the particle trajectories collapse, and in other words, they stay random. So there in that intermediate range, you get only fragile spontaneous stochasticity also for the Kryknon model. Okay, now we don't have, I don't know, how much time do I have? How much? 10 minutes, okay. So let me try to say a little bit about general methods for understanding spontaneous stochasticity. 20? 20, okay. Okay, so let me try to say a little bit about general methods for understanding spontaneous stochasticity. So for physicists, as soon as you say the word universality, what immediately pops into their mind is renormalization group. And indeed, renormalization group seems like a very natural method to assault this problem, under the situation that there's some natural scaling symmetry. So the renormalization group methods that I'm going to talk about in these lectures, there actually have several that have been developed for this problem. But all of the underlying assumptions are that the models have some kind of scaling symmetry. As we actually saw in some of the earlier lectures, that's actually true of many equations of fluid mechanics. So we're lucky that many equations of fluid mechanics do have some natural scaling symmetries, and that makes it very promising for those problems to try to do a renormalization group approach. So here I'm just going to describe very briefly a renormalization group approach that I used, and used it to study the simple toy problem. So this is work with Dima Bandak, who was a student of Nigel Goldenfeld. And in fact, the renormalization group method that we use here is built on the use of renormalization group for the long-time behavior of PDEs that was developed back in the 1990s by Goldenfeld and collaborators, and also by Brichmont and Kupiainen in the math community. And these renormalization group methods were designed to study the long-time asymptotics of deterministic PDEs. So the reason that's relevant for this problem is that the long-time behavior of this solution, since I'm looking at a stochastic differential equation, is determined by the Fokker-Planck equation. And what I'm really interested then is understanding how this Fokker-Planck equation at long time develops a universal form and forgets the precise initial data. So it's exactly the kind of application involved in this old renormalization group theory that was developed by these authors. Okay, so this I'm going to discuss the same toy problem. This is a regularized version of this velocity field here, where this h is some value between 0 and 1. You'll notice that if I set this regularization parameter L to 0, I get exactly this model when I set delta equals 1 minus h. So this is the analog of viscosity for this model, this L. And simultaneously, I'm going to have diffusivity. And what we want to consider is what is the limiting probabilities of the trajectories in this model when I take L and D going to 0 together. First of all, I should tell you that when we look at the limiting dispersion of the trajectories, as we let the noise get weaker and weaker, holding the ratio, that's the so-called Schmidt number, nu over d, when I hold that fixed and I take the limit of long times, then I forget the value of the Schmidt number at long times, exactly what I saw in the turbulent case with the database. Yes?
So here, a universal field is just, say, with respect to the initial data and not with respect to the regularization.
So I didn't say anything about, well, there's only one velocity realization.
Yeah.
So, what I have is, I have not said anything about universality yet. But I'm just setting up the problem. What we will see actually in this problem, if I take random initial data that's symmetric around the origin, then it's completely universal.
Yeah, but you need the symmetry.
You need the symmetry. In fact, what we did is,
Here is a bit of the universality. If I change the symmetry, then I change.
that's right. Actually, in this case, in the language of physics, there's a continuous line of renormalization group fixed points. So this is a very standard thing that happens in some statistical mechanical models, like the 8-vertex Baxter model. You have not just one fixed point, but a whole continuous line. And you always break down universality then. And that's exactly what happens. Now, in this example, we can find all of those fixed points, and we have completely classified their domains of attraction. So you give me the initial data, and I can tell you exactly where it's going to end up. But except for the universality with symmetric initial data, it's very fragile. And it depends on exactly how I take the limit. But we can completely, renormalization group not only tells you if there is universality, it also tells you when it breaks down. And if it breaks down, it's supposed to allow you to tell you the particular domain of attraction of every fixed point. So it's a tool that goes beyond just proving broad universality. It's a precise method for analyzing breakdown of universality as well. Okay, so I should mention, by the way, that there was some prior work on this, a lot of prior work on this in the probability community, in particular Flandoli. And Flandoli had done very similar scaling arguments to this, but with one crucial difference. All the probability literature, as far as I know, set L to 0.
And if you change the noise,
Pardon?
here also you take the noise, the Gaussian noise again.
This is white noise. Eta is Gaussian white noise.
Yeah, and if you change the noise, do you...
So the noise, that's exactly, the noise is going to go to 0 because I'm going to take D going to 0.
Sure, but I can imagine to take another stochastic process.
Another what?
Stochastic process instead.
Another process, another random process. Yeah, in fact, this is something I'll also talk about later, like if you switch this to fractional Brownian noise. Okay, and we don't have as complete an analysis of that yet, but I was looking at that with Leonie Canet using functional renormalization group methods. Within a certain range of Hurst exponents of the fractional Brownian motion, you get the same behavior as this. But if you take the Hurst exponent too big, several things successively change. There's actually 2 transitions. But anyways, here I'm only considering, in this case, the white noise. The reason for that is only for the Markovian case that I can turn this into a PDE problem, because then I have forward Kolmogorov equations. In the fractional Brownian, I can't use that method, and that's exactly why you have to use more sophisticated techniques then. Okay, but I want to show you just one example where we can analyze this. So for physicists, the key idea here is that, you know, in critical phenomena, what you do is you say, okay, the small scale details are irrelevant. What I see at large scale should be independent of what the details of the microscopic Hamiltonian are at small scales. So what you do in Wilson renormalization is you integrate out the small scales. And then you iterate, and under successive iteration, you ignore the small scales and you rescale. You integrate out the small scales and you rescale. You go to an asymptotic fixed point, which is the same for a very large class of small scale models. The same idea is used here, except now what we do is we integrate out the early times. And this is actually a little bit bizarre if you think about it. The correct way of solving the initial value problem for this class of models is to ignore the precise initial data. You want to solve the Cauchy problem by not looking at the precise initial data, because the precise initial data don't matter. And so what you actually do is you integrate out the early time history of the problem, and then you rescale. You integrate out the early time again, and you rescale. What you then get are new effective initial data. So you take this window time is arbitrary. The important thing is this parameter b. B is our renormalization group flow parameter. And what we're doing as we increase b is we are integrating to longer and longer times and rescaling. And then this is the analog of a Kadanoff block spin. And if renormalization group works, then this new effective initial data should have a limiting fixed point distribution when I choose this renormalization correctly. By the way, for physicists, sorry, there's no anomalous dimension in this problem. You can actually get the field strength renormalization from dimensional analysis. It would be interesting if there are models where there's an anomaly, but in this case, there's no anomalous dimension. So in any case, the renormalization group procedure is you get new effective initial data, you get a new effective drift field. If you think about what happens as b gets larger, this velocity field under the renormalization group flow is getting closer and closer to singular. Likewise, under this renormalization group flow, the noise is getting weaker and weaker. And so in the limit, you go to a fixed point in which you get deterministic dynamics, just given by that singular velocity field, but with new effective random initial data. And the renormalization group flow equations actually become partial differential equations. Here are the RG flow equations. In this case, because this is essentially Fokker-Planck equations, you can study it in gory detail just by using eigenfunction expansions for the Fokker-Planck operator. And so you have complete control of these equations. We very understand in fine detail what the solutions look like by using eigenfunction expansions. And you can completely classify all the fixed points, all their domains of attraction. You can even calculate the rates of approach to the fixed points, which, by the way, gives you interesting singular large deviation theory, which is different than Friedland-Wenzel theory. And I should mention that had also been noticed previously by Gradinaro et al. In the probability literature about 15 years ago, but only for the case where the velocity field is actually singular. Here we derive it for the case where the velocity field is only quasi-singular. As Laurent said, it's Lipschitz at every stage, but the Lipschitz coefficient, the Lipschitz is getting weaker and weaker. The Lipschitz constant is blowing up as we let b go to 0. Okay, so here in this model, the spontaneous statistics is actually very simple. And in fact, even though there is a continuous infinity of solutions for this problem, because my trajectory can stay an arbitrary amount of time at the origin and then leave, the limiting statistics are very simple, and the trajectories immediately leave the origin, and they simply go with some probability to the left and some probability to the right. So the limiting statistics is actually very trivial. It's just a sum of two delta functions. But again, the renormalization group theory tells you exactly how to determine the probability of one spike over the other, the rate of approach to the limiting solutions, etc. Okay, there's another RG approach, which I'll talk about in my next lecture in detail for what's called Eulerian spontaneous stochasticity. Okay, now for physicists, this actually also goes back to the question Laurent answered. We made a phase diagram because physicists like to think of this in terms of a phase diagram. So the Reynolds number controls the singularity of the velocity field. The higher the Reynolds number is, the more singular the velocity field is. The Peclet number controls the noise strength. So as the Peclet number goes to infinity, the system is becoming less and less noisy. And what you find is that when you can take the limits, as was asked earlier, in many different ways. If in fact, in this model, you take the noise going to zero super exponentially in the diffusivity, you do not see spontaneous stochasticity. Then you see this deterministic behavior. In the other limit, if you take the Reynolds number to infinity, but you keep the noise strength large, well, then you just see pure random noise. But in this broad swath green area, that's the area that's governed by the spontaneous statistic. By the way, we used as the order parameter here the variance of the particle separation between the two solutions. That's actually what's being plotted here. The deterministic case has no variance. There's just one particle trajectory. Here, it stays very large because it's completely determined by the external noise. And this green region is where you're seeing the spontaneous statistics. And again, in this broad range of parameter values, you see the spontaneous statistics, no matter how you're taking the limits, as long as you're in this green region. And also, long before you go to the infinite Reynolds number limit or the infinite Peclet number limit. So you do not have to go to infinite Reynolds number or infinite Peclet number to see spontaneous stochasticity. You see it at finite Reynolds and finite Peclet numbers as long as they're sufficiently large. Okay. I think I'm going to go over the rest of this pretty quickly because I don't have a lot of time. Let me just say why Lagrangian spontaneous stochasticity matters. Well, in addition to the scalar equation and the Feynman-Katz representation, there are also similar stochastic representations for the Navier-Stokes solution itself. And in particular, Constantine and Eyink, in a paper in 2008, gave a very elegant formulation of such a stochastic Lagrangian representation for the solution of the Navier-Stokes. In this case, like in the scalar case, you have to solve for the stochastic Lagrangian particle trajectories backward in time. And the reason for that is that the Navier-Stokes equation is parabolic. It's ill-posed backward in time. It's well-posed forward in time. Well, mathematicians won't even agree with that because we don't fully know that. But Constantine and Eyink, in this case, assume strong solutions. Okay, so that means that the Navier-Stokes solution is determined by its initial data. And therefore, what you have to do is you have to calculate at a given point x and t, you have to go backward in time along these stochastic trajectories to sample the initial data. And they determined this nice stochastic representation formula for the Navier-Stokes solution, where again you have to take a gradient of the flow map of these stochastic flow maps. This is actually a generalization of what's called the Weber formula. It's actually well known for Euler equation in a deterministic setting. And they gave a stochastic representation of this. I think a more intuitive way of looking at this is in terms of the Kelvin theorem, is that they showed that there's actually a stochastic version of the Kelvin theorem. If I want to know the circulation on a given loop C at time t, what I do is I follow these stochastic trajectories back in time to the initial data. I now find where that loop at time c was at earlier time under these stochastic flows. I calculate the circulation on that loop with the earlier time velocity at that earlier time loop. And when I average over all those circulations, I get the circulation here. That's a theorem for Navier-Stokes equation. And in fact, not only is this true for Navier-Stokes equation, it is characterized by that. The only incompressible fluid velocity that has this backward martingale property for the circulations are solutions of incompressible Navier-Stokes. Okay, so this is actually a generalization for the nonlinear Navier-Stokes of what I discussed for the scalar problem. Another way of looking at this is in terms of vorticity. If I look at the usual Cauchy formula for vorticity for the Euler equation, if you get rid of the expectations and if I follow along deterministic trajectories, then this is the well-known Cauchy formula for Euler equation. And what Constantine and Eyink showed is that this generalizes to Navier-Stokes at the expense of making the trajectories random and solving this backward Ito equation here. And then, if I plug that solution of those backward Ito equations into this formula, and I take the expectation, that gives me the Navier-Stokes vorticity field. So you actually can generalize the Cauchy invariant of Euler equation to be a stochastic Cauchy invariant for Navier-Stokes, in which this quantity here is a backward in time martingale in terms of that time parameter S. Okay, so these comments are just to say that the non-uniqueness of the Lagrangian particle trajectories in a turbulent flow will have important consequences not only for passively advected scalars, but for the solution of the Navier-Stokes equation itself. Okay, because you cannot expect that Kelvin theorem will be holding better and better in the limit of very, very high Reynolds number, by the way, as Taylor did in a 1938 paper. You cannot hope that that will be true because the advected loops will have no reason at all to ever approach a single loop. They will stay random. So here, in fact, I illustrated this stochastic transport of vorticity by a diagram. And the way that you actually implement this is if I want to know the vorticity here, I go backward in time along these stochastic trajectories. Well, actually, I create these stochastic trajectories. Then I go to the starting time. Along each one of those stochastic trajectories, I do a quasi-Lie transport of the vorticity. This is not a real Lie transport because I'm not advecting along deterministic trajectories of the Euler flow. I'm solving this ODE along that particular stochastic trajectory. Okay, now when I solve that, these vector fields evolve into this. When I average those over all the trajectories, that gives me my limiting vorticity. Okay. The same idea applies to MHD. In fact, this is an application of the same principle. This came from a Nature paper that I published many years ago, showing that as a consequence of this Lagrangian spontaneous stochasticity, in a turbulent MHD flow, the usual flux freezing principle cannot be valid. And in fact, what you see is that in the limit of very, very high magnetic Reynolds numbers and high kinetic Reynolds numbers, the particle trajectories stay random. And so this stochastic flux freezing still remains true, but you have to average over this whole ensemble of backward stochastic trajectories to get the correct magnetic field. Ideal flux freezing does not work at all in the usual conventional way in the infinite magnetic Reynolds number limit. Okay, so this is actually my last slide. One of the questions is, can you have spontaneous stochasticity beyond turbulence? So everything that I said so far has been about some variety of turbulence, but you might, I did throw in occasional references to more general theory of ODEs, like the Crippa-Ambrosio work on the superposition principle. And so a natural question is, could you in fact have spontaneous stochasticity in other ODE systems where in some limit the velocity field becomes singular and you lose unique trajectories? Well, I think this is an interesting question. It's been examined in some special cases. So Dima Bondak in his PhD thesis at Illinois made a very simple mechanical model of an infinitely jointed pendulum. Well, it's actually finitely jointed, but in the limit, it becomes infinitely jointed. And in that simple mechanical pendulum model, he was able to observe numerically spontaneous stochastic behavior. So you can make very simple mechanical models in which that happens. I'll also mention that, I'll actually discuss this a little bit in my last lecture. You can even see this in Hamiltonian particle trajectories. for example, in the semi-classical limit of quantum mechanics. And then you can see spontaneous stochasticity in simple toy models, which is triggered by quantum fluctuations. Okay, so there seems to be a big possibility for spontaneous stochasticity, not just in turbulent flow, but in many other problems where you get non-unique limiting solutions as some parameter is varied. Okay, so thank you, and I'm glad to take questions.
Maybe some short questions. There are many.
Yes. Well, that was the question that was asked earlier. So it depends. If you take the limit as d goes to 0 first, then yes, you have unique particle trajectories. But in that case, if you let the initial data be random, and you let the randomness in the initial data go to 0 together with nu, then you can still get spontaneous stochasticity. In fact, in that simple toy model that I analyzed with renormalization group, that's exactly what happens. So if I take d going to 0 first, but if I keep my initial data random, and then if I let nu go to 0 and the initial data go to 0 together, I still get spontaneous stochasticity. That's also what happens in the quantum case. If I take the quantum case, I look at the initial wave packet tending to 0, while I also let h bar over m go to 0. And in that case, I get limiting randomness coming from the non-unique solutions of the Hamilton's equations of motion. But I can get it even with deterministic dynamics, like Navier-Stokes, if I let the initial data be random. So even on that side of the parameter regime where, so in my phase diagram, there should be another axis. I should have a third axis coming out of the screen. The third axis would be the variance of the initial data. And then even along this line here, where way up there, where the Piclet number is infinite, that means I have no randomness at all in the dynamics. The randomness in the initial data would be enough to create spontaneous stochasticity. And that's known for the Kryknen model. It's also true for this model, and it comes out of the renormalization group analysis. So we know in many examples, random initial data is enough to do it, even with deterministic dynamics. Yeah. Actually, it would be better if you had the microphone because I can't quite hear you. But sorry, I'm getting old, so my ears are weak.
There is a link between your renormalization group approach and singularity formation when at the singularity the solution is a self-similar solution and does not lose the dependence of on the initial data in some.
So you're saying that there's a theory of renormalization group by whom? I didn't understand your question. I'm sorry.
Okay, because you say that we lose the information of the initial data.
Yes, we do.
But in some cases, in singularity formation, there is a...
Oh, actually, absolutely not. I mean, I'm not claiming that you always lose information of the initial data, far from it. That's not going to be always true. I'm not claiming that this is a universal phenomenon.
Okay.
What I am claiming is that if there is anomalous dissipation in the scalar, it must happen.
Okay.
Okay, so I'm not saying that we know that if I take a standard chaotic system, and there are lots of simple mechanical models that are modeled, for example, by standard smooth chaotic dynamics, well, none of this would apply. And it's also possible that you could even have limits in which the velocity field becomes rough, but this doesn't apply. Okay, so as we saw here, there are even cases where sometimes the limiting spontaneous statistics are you do have unique spontaneous statistics, and other cases where it's fragile, and depending on how you take the limit, you'll get different random distributions. So there's a whole smorgasbord of possibilities. But the point is that if you want to understand anomalous dissipation of the scalar in a turbulent flow, this must happen. This is the only way. This was exactly the main point of Gawędzki et al. This is the only way it can happen. There's no other. The only way that you can get anomalous dissipation of the scalar away from boundaries, boundary layers could be another possible mechanism, but away from boundary layers, the only way it can happen is through this breakdown of uniqueness, and that's a theorem.
Okay, yes.
Okay, maybe we can stop here. Greg will be here the next few days, so if you have any questions.
No.
Thank you again.